So let us now derive the OLS point estimator that we need for the rest of the course over and over again. So we have already defined our vectors and our matrices one more time. So our y vector is t by 1. We have our x matrix. Our x matrix has the dimension t by k plus 1. We have our disturbance vector, our epsilon vector, defined as element t by 1. It's a t by 1 vector. And we have our beta, our parameter vector, which is k plus 1 by 1 vector. Yeah? So we have already defined the dimension of our data vectors or data matrices, and the OLS methodology has the objective, so the function is that we minimize the sum of squared residuals, and in vector notation it is epsilon prime times epsilon. Yeah? We minimize the sum of squared residuals, and which is the scalar product of our residual vector epsilon prime times epsilon. Yeah? So epsilon prime, it's 1 by t times something that is t by 1. So of course what comes out here is a scalar. Yeah? 1 by 1 is a number. It's a scalar. Okay? Knowing that our model is defined as y is equal with x times beta plus epsilon. So that's our linear model, how we defined it. And we know now our y vector, yeah, that's a portfolio of stocks, or it can be different stocks, so it depends. I will now skip the subscript I here. Yeah, so we have just one vector epsilon here, y, sorry. And our X matrix consists of our regressors, of our risk factors. Yeah? In the capital asset pricing model, as we spoke about, we have here a vector of ones, and in the second column we have the excess market returns. Yeah? Time 1, time 2, and here the last one, the excess market returns at time capital T. So that's how our X matrix would look like in the case of the cap M. So, and our vector of disturbances, we have already talked about that earlier. So what we can do is now, in this expression, we can plug in what we have here. So if we solve this equation for epsilon, it's nothing else but y minus x times beta. Yeah? So we plug in simply this expression here. So our function becomes then a minimum of y minus x times beta transposed times itself, y minus x times beta. So that's our objective. That's the objective function that we have to solve, or that the OLS point estimator aims to solve. So if we transpose, so the first step is that we transpose what is here in the parentheses. So what we do is we transpose first the y vector minus x times b transposed, and we know from linear algebra, if we have a matrix product A times B transposed, what we have to do is we have to change the order of matrices, right? So this is basically B transposed A transposed. Okay, so we apply this simple rule here as well. So what we have to do is then, what we have is then B transposed X transposed times what we have here times Y minus X times beta. Next we have to multiply it out. So what comes then is Y transposed times Y plus Y transposed minus X times beta, so this becomes minus then, minus Y transposed X times beta, minus this term here times Y, minus beta transposed X transposed times Y. This guy times this guy, minus times minus becomes plus. So what we have here is plus beta transposed X transposed X times beta. So we have just multiplied out the parentheses after we have transposed the elements of the first parenthesis here. So what we see now already here, this first guy here, Y is a t by 1 vector, Y transposed itself, so this is 1, if we transpose a t by 1 vector, it becomes 1 by t. So what we have here is 1 by t times t by 1, this is 1 by 1, that's a scalar. That's a scalar, this is 1 by t times something that is t by k plus 1 times something that is k plus 1 by 1. So what comes out here is also 1 by 1. It's also a scalar. That's a scalar. And what we have here, that's also a scalar. And of course it must be like that, because what comes out needs to be a scalar. It needs to be just a number. So what else can we do? So we can simplify this expression a little bit, because this is a scalar and this is a scalar. So this is the same number here. So what we can do is we can rewrite it like Y transposed Y, so this remains the same, minus 2 times, and we take this expression here, 2 times the beta transposed X transposed Y plus this guy here, beta transposed X times beta. So, and because we have to minimize this expression here, what we have to do now is we have to take the derivative. So we have to take the derivative with respect to beta. So let's now move this up again. Let's take this away. Let's move this equation up here. Y transposed Y minus 2 times beta transposed X transposed Y plus beta transposed X times beta. So we have just moved up this equation up. We moved this equation just up. So, and now we have to take the derivative from this expression here. The derivative of this equation with respect to beta. So, and what is that? So the first guy here, Y transposed Y, there is no beta. So if we take the derivative, this becomes 0. So we can skip that. The second part of the equation, minus 2 times beta transposed X transposed Y, if we take the derivative with respect to beta, what remains is minus 2 times X transposed Y. Because this beta, obviously, if we take the derivative, this disappears. So what remains is minus 2 times x transposed y. And if we take the derivative with respect to beta from this last term here, what remains is 2 times x transposed x times beta. So and that's the rule from linear algebra. So you can basically multiply this out and you will see, if you, for instance, if you take the our matrix as we have defined it earlier, if we take the X matrix how we defined it in the case of the cap M, and then the beta vector would just contain obviously 2 parameters, the alpha and the exposure against the market vector. So you can take this at home as a homework and multiply this out. Yeah, for capital T observations, you can take any t, let's say 5 or something. You create these matrices and take the derivative with respect to beta. What you will see is what comes out is 2 times x transposed x times beta. Yeah. So and we have to set these equal to 0 because we have to minimize it. Yeah. We set this expression equal to 0. So first of all, what we can do is we can cancel out the 2. 2 cancels out obviously because it's on both sides of the equation if we move this guy on the other side. So we can take away this 2 here. What remains is minus x transposed y plus x transposed x times beta. Let's take this guy here on the right hand side of the equation. What remains is x transposed x times beta, and now we have to give it a beta hat because now it's an estimate, is equal to x transposed y. We have put this now on the other side of the equation. And what we have to do now is, in order to get the beta, what we have to do is we have to get this x transposed x on the other side of the equation. And how do we do it? Well, we take the inverse. So what we have to do is we have to multiply this equation by x transposed x inverted. And now you remember why it's important that the column vectors are not perfectly correlated, because if they would be perfectly correlated, we couldn't take the inverse of that matrix product. So let's do that. Let's take the matrix product. What happens here is, okay, x transposed x inverted times x transposed x times beta hat is equal with x transposed x inverted times x transposed y. Okay, so what we know from linear algebra courses, if we have any matrix, let's call it A, matrix A times A inverted is the identity matrix. And the other way around as well. If we multiply a matrix A inverted times itself, what comes out is the identity matrix. So we apply this simple rule here in our context as well. So what happens, what remains here is the identity matrix. So this guy here is the identity matrix. And what we also know, another rule from linear algebra is, if you multiply the identity matrix with a matrix A, what comes out is matrix A. So anything, so the identity matrix doesn't change anything. So we apply this rule here as well. So what comes out here is the identity matrix times beta hat is beta hat. So we can take away this guy here. This becomes the identity matrix. So what remains is our beta hat, our well-known OLS formula, is given by the regressor matrix X transposed itself inverted times X transposed Y. Yeah? That's our well-known OLS formula. And that's now very important to know, because this formula we will use basically all the time, more or less. So this is what you definitely need to write down, because we will come back to this all the time. Let's take this away for now. So the next thing that is important for us, we have to talk about the properties of our point estimator. Yeah? So we have to know how good is our point estimator. Yeah? So what's the expectation? So what can we expect? Okay. So what's the expectation of our point estimator, and what is the covariance matrix? So we need to know the covariance of our point estimator, so that we can make correct inference. So the first question is then, what's the expectation? Yeah. So again, our point estimator is given by, so B